Testing. Okay, let's get started. Answer your next, please. Barat. Here. Bessie. Here. Burke. Kane. Dunlap.
Here.
Gallegos. Here. Head. Irvin. Leonard. Medina. I'm sorry, Kylie Medina. Manuel Medina. Here. Benisi. Monsieur is here. Olano. Jasmine Richardson is here. Sieg. Here. Tillman. Here. Venture Pagana. Here. Weflen. And the right. All right, so we're going to continue our discussion of equilibrium. And what I'm going to start talking about is a very important law or principle when it comes to this topic. And that principle is and I must apologize if there are any French speakers inside here, because I'm quite sure I'm going to massacre the pronunciation of this person's name. I think it's pronounced Le Chatelier. I'm used to just saying Le Chatelier, but I think the correct pronunciation is Le Chatelier. So if you hear me slip back into pronouncing it differently, please forgive me. Okay, so this deals with systems, chemical systems, in a state of dynamic equilibrium where it's already in equilibrium, and then you do something to disturb the equilibrium. What this principle does is help you to predict how the system will respond to whatever sudden changes that one may impose on a system that is already in equilibrium. And if you look in different textbooks, you see that, the principle is worded in different ways. The way it's expressed here on the screen is when any change in concentration, temperature, pressure, or volume is imposed on a system at equilibrium, the system will respond by attaining a new equilibrium condition that minimizes the impact of the imposed change, right? So it's a bit wordy, but basically that's what this principle says. The way I look at it, or if I were to put it in my own words, I would say that if the system is already in a state of equilibrium and you impose any change on the system, then the system will respond by opposing the change that you impose. That's my way of stating it, right? So basically what I'm saying is, system is already in equilibrium, you change something about it, and then the system will respond by doing the opposite of the change that you have imposed on it, right? So that's basically my way of expressing the principle, all right? And we kind of had an introduction to this particular principle in during the last class when we talked about the reaction quotient, right? So what we're going to look at is what will happen if we change the amount of a particular species involved in the system already. Now, remember we said that the reaction quotient is the basically, to summarize, it's the concentration of the products divided by the concentration of the reactants, right? At any time, okay? And at equilibrium, that ratio will be equal to the equilibrium constant, right? Now, if the concentration of one of the reactants, let's say, is increased, so let me just scribble out something here just so that we keep this in mind. So basically, Q, which is equal to Kc, I'm just going to write here, Qc is equal to the concentration of products divided by concentration of the reactants, all right? So let's say that you increase the concentration of one of the reactants, which means that this part here will increase, right? So let's say we started off with this system already at equilibrium, and then you increase all of a sudden the concentration of one of the reactants. Then, so let me just say that concentration of reactant increases, right? Then what's going to happen is that QC will now be less than KC, right? Which means that the system is not at equilibrium, right? So QC is now less than KC. So the system by itself will naturally try to restore equilibrium. So the question now becomes how the system does that. Now remember, the equation for the reaction would be reactants in equilibrium with products, all right? So if you think about this, if QC is less than KC, the question now becomes, how do we get QC back to being equal to KC? So basically what we have to do is, or what the system will do, is try to increase the value of QC so that it becomes equal to KC. So how does it do that? And the answer is that the reaction will shift in this direction, right? In other words, some of the reactants will react to form more products so that the concentration of the products will increase and the concentration of the reactants will decrease, and therefore the QC value will now be equal to the KC value, all right? So basically, as I just said, the concentration of the product will increase, which means that the equilibrium will have to shift to the right. And therefore, once the product concentration increases, and there will be a corresponding decrease in the concentration of reactants, then QC will be equal to KC, all right? So that's basically an example of Le Chatelier's principle, because the principle says that the system will respond by doing the opposite of what? The change you impose on the system. If you reduce the concentration of the reactants, then the system will shift the equilibrium position so as to increase the concentration of the reactants so that the QC will now be equal to the KC value, all right? Now, let me just give a real example of this particular type of observation. Now, what we're looking at here is a graph representing the changes in concentration with time for this reaction I'm about to write. CH3, CH2, 6, CH2, OH. So this is known as 1-octanol. And then this is going to react with acetic acid, which is CH3, CO2H. So this is acetic acid. And the product of this reaction is octyl acetate, which has this formula, CH3, CH2, 6, CH2, OH. I'm sorry, not OH, OC, OO, CH3. In fact, let me abbreviate it a bit. Make things a bit simpler. Just going to put O2 here. So O2, CH3 plus water. So this is the reaction we're concerned with when it comes to this graph, right? So basically, if we're starting at time 0, we have a certain amount of acetic acid and a certain amount of 1-octanol and none of the products, all right? So basically, the reaction will take place between the 1-octanol and acetic acid. And of course, one would expect that the concentrations of both of them would decrease. Simultaneously, because these are the product form, the concentration of water and octyl acetate will increase until you reach a state of dynamic equilibrium where the concentrations remain constant for all the substances involved, right? So basically, from here to here, we have dynamic equilibrium where the rate of the forward reaction is equal to the rate of the reverse reaction, all right? Now, somebody decided to add a certain amount of one of the reactants to the system which is already at equilibrium. So this person decided to add acetic acid. So at this point, which is the time at which the acetic acid is added, the concentration of acetic acid will jump, of course, suddenly, right? So the system at this point, upon addition of the acetic acid, is not at equilibrium anymore. So based on what we just discussed and based on Le Chatelier's principle, what will happen is that some of the acetic acid will react with some of the 1-octanol. So both concentrations will fall. And at the same time, you're going to have an increase in the concentration of octyl acetate and water, right? And then what will happen? You're going to achieve a new state of equilibrium where the concentration of acetic acid, the 1-octanol, the octyl acetate, and water remains constant, right? So basically, Le Chatelier's principle will predict that this will happen because if you add a reactant, in this case acetic acid, then the system will try to decrease the concentration of the acetic acid. So it's going to use up some of the acetic acid that was added, and therefore, eventually, you're going to end up with a new equilibrium position for the system, all right? So that's basically what is happening here. So I stated here, the concentration of the products will increase, the concentration of reactants will decrease until you get, as I said before, a new equilibrium position, all right? So that's basically how that works when you are increasing the concentration of one of the reactants. And based on this, one can also rationalize what would happen if you were to decrease the concentration of a reactant or product. In fact, the next slide is an example of such a situation using the same reaction that we just looked at, right? So this question says, water can be removed from an equilibrium mixture in the reaction of 1-octanol and acetic acid, for example, by using a solid drying agent that is responsible, or insoluble, I should say, in the reaction mixture. So the question says, describe how the removal of a small quantity of water affects the equilibrium. So in this particular question, what they're saying is that you have the system already in equilibrium, and you continually remove the water from the system, all right? So we can use Le Chatelier's principle to explain that, right? Basically, when you remove the water, of course, you're decreasing the concentration of the water. According to the principle, the system will respond by doing the opposite of what you're doing. So if you're removing the water, then the system will try to produce more water. in order to reestablish equilibrium. So the question is, which direction will the equilibrium shift to produce more water? And the answer is the equilibrium will shift from left to right. In other words, it's going to shift such that some of this will react with some of the acetic acid, and that would facilitate the formation of water. All right? So that's basically how we can use Le Chatelier's principle to make predictions as to which direction the equilibrium will shift when you either add something to it or remove one of the components of the mixture. And in this particular case, this is a very common practice in organic chemistry. Again, for those of you who have to do organic chemistry, where you might have a product that you want to isolate, or you want to favor the formation of one product, and there's a byproduct that is produced, and you know that the system will be in equilibrium, then you add something to remove this which you don't want, and that would push the equilibrium to favor this, which is what you want, and therefore you can maximize the yield of that product. All right. Also, you could increase the concentration, as we saw before, of this or this, well, I should say and or this. So basically, by increasing the concentration of one octanol and acetic acid, you can also favor the formation of your product. All right. Now, if you remember, I talked about the Haber process in the previous chapter, kinetics, right? You know what, let me just create a blank slide here, because I want to further emphasize how Le Chatelier's principle works. So let me introduce a slide. If you recall, the Haber process is used to make ammonia. And the equation for this reaction is N2 plus H2 to give NH3. And to balance this, we need a 2 here and a 3 here, right? Now, if you remember, we talked about heterogeneous catalysis in the previous chapter. And remember, I said that this guy by the name of Haber, who was a Jew, right? He basically came up with a lot of, or he tried and tested, and of course, you would experience some failure, different catalysts in order to favor this reaction, in order to speed up the reaction. Another thing that he looked at was basically how to push the equilibrium in that direction. And he employed some aspects of Le Chatelier's principle plus other things, which we're going to discuss later on. So basically, what he did, in order to favor the formation of ammonia, he increased the pressure of this, which is tantamount to increasing the concentration. He did the same thing for the hydrogen as well. So basically, by increasing the concentration of both nitrogen and hydrogen, again, according to Le Chatelier's principle, that would push the equilibrium to the right, because the system will try to reduce the concentration of both components, and therefore the only way the system can do that is to shift to the right. So let me just put this in words. How should I start? Okay, let me do it this way. If the change that you're imposing, right, is to increase the concentration of nitrogen and hydrogen, then according to Le Chatelier's principle, the system will respond by decreasing their concentrations and therefore the equilibrium will shift to the right, favoring the formation of ammonia, right? So that's basically what will happen if you increase the concentration of nitrogen and or increase the concentration of hydrogen, right? The system will respond by doing the opposite of what you're trying to do to the system, So if you're increasing those two components, the system will try to decrease those two same components to reestablish equilibrium, and therefore the equilibrium position will shift to the right, and therefore what will happen is that more ammonia will be formed, which is basically the aim of this, to make ammonia or to make as much ammonia as possible. All right. Now, there's one more thing you can do, and this is all related to changes in concentration. There's one thing you can do, or one additional thing you can do to favor the formation of ammonia. And I want you to tell me what that is, which is not involving changing the concentration of nitrogen and hydrogen. What can you do in addition to what I just mentioned, what I just discussed? What else can you do in order to favor the formation of ammonia? Again, this is based on Le Chatelier's principle. Yes, sir. Exactly. You remove the ammonia, you decrease the concentration of ammonia, and then the system will respond by producing more ammonia, right? And therefore will shift to the right. So that's another thing that you'd have to do when it comes to facilitating the manufacture of ammonia using this method, all right? So I'm mentioning all this because these are the considerations that scientists and engineers have to take into place when they take into consideration, I should say, when it comes to manufacturing compounds, right? Especially when it comes to equilibrium systems. You have to basically choose a set of conditions which will help you to maximize your product, right? And that's based on the balanced equation, and that's based on the Chatelier's principle. And concentration is just one of those factors that you take into consideration. The other thing you have to take into consideration is how fast the reaction goes. And that's one of the things that Haber looked at. And that's why he developed, several different types of catalysts in order to not only maximize the amount of ammonia, but also to make as much ammonia quickly as possible, all right? Okay, so let me just add, since he answered the question, let me just say that, you know what, let me erase all this here so I can more clearly write down what we just discussed. Okay, so if you're imposing the change, if the change imposed is removing ammonia or removing NH3, so that corresponds to a decrease in the concentration of ammonia, which means that the system will shift to the right to produce more ammonia. All right, and that's it. Again, based on Le Chatelier's principle. All right. Okay. Any questions so far? Any questions? Any questions? No questions? Okay. So let's delve into some more aspects of Le Chatelier's principle being applied to changes in the amount of any component in the system. So we're going to look at now what we call heterogeneous equilibrium. Basically what that means is that you have different substances involved in the system, but they're in different states, all right? So you can have a situation where you have a reaction where solids and gases are involved, such as this example right here. Now, the actual reaction that this is dealing with is the decomposition of calcium carbonate solid to form calcium oxide solid plus carbon dioxide gas, all right? So this is an example of a heterogeneous equilibrium system because you have solids and gases involved, right? Now, let's say you start off with a certain amount of calcium carbonate and then it decomposes. So usually when you're decomposing something, some amount of heat will have to be applied, right? So that's what is happening here. Heat is applied to this, and then eventually you're going to have some carbon dioxide present in the system. And calcium oxide is, of course, another product of that decomposition, right? So eventually you're going to have an equilibrium. So let me draw the other arrow here. You're going to have a system in equilibrium where the back and forth will take place, right? Now, let's say you add from here to here, you add some calcium oxide, right? What you'll find is that there'll be no change in the amount of carbon dioxide that will be present. And you might be wondering why, because if you remember what we talked about just earlier, changing the concentration of one component should change, everything in terms of the equilibrium shift and so on. Well, if you recall, yesterday, I said that when it comes to solids and liquids, if they're involved in reactions such as these, their concentration doesn't change, right? So if the concentration doesn't change, even if you add more of that same substance, then that will have no effect on the equilibrium position, and therefore the amounts of substances, especially the carbon dioxide gas, will not change, right? So therefore, there's no change in the pressure of the carbon dioxide when you add some calcium oxide. And the same is true if you're adding calcium carbonate, which is also a solid. Again, there'll be no change in the amount of carbon dioxide, and therefore the pressure will not change for the same reason, all right? So that is true if you add more solids, and also if a liquid is involved, if you add more liquid, same thing is going to happen. There'll be no change in the equilibrium position or no change in the amounts of any other substances that are involved, all right? So that's basically what will take place as far as the heterogeneous equilibrium is concerned. Adding any amount of solid or liquid that is involved in such systems will not affect the composition of the equilibrium mixture. All right. Now let's look at what happens when it comes to gases. And we're going to look at it we're going to look at this topic here in two ways. Well, first, let me just say this. So this will apply to systems that have gases as a part of the whole system, components in the system, right, at equilibrium. Now, we're going to look at it in two ways. We're going to look at it in terms of what will happen if we change the pressure of only one gas in the system, and then what will happen if we basically change the pressure of the entire system, all right? So let's look at what happens if we have a system where a gas is involved and we change the pressure of that one gas, all right? So according to what you see here on the screen, when you change the pressure of one gas, let's say you increase the pressure of one gas, right? Then you should recall that from your general chemistry 1, the pressure of a gas is directly proportional to the concentration of that gas, right? So basically, changing the pressure of the gas is basically the same thing as changing the concentration of that gas. So if you increase the pressure of the gas, you're going to increase the concentration of the gas, right? So let's say, for example, going back to this reaction here, right? 3 here. And let's say you increase the pressure of nitrogen. That means you're also increasing the the concentration of nitrogen. So how will the system respond? Which direction will the equilibrium system shift?
To the right.
To the right, exactly. So therefore, equilibrium will shift to the right. All right? So therefore, the concentration of ammonia will increase, and the concentration of the nitrogen and hydrogen will decrease. All right? So that's basically what will happen. Now, of course, you can rationalize what would happen if you decrease the pressure of nitrogen, right? So that means that you're decreasing the concentration of nitrogen. So which direction will the reaction shift? Equilibrium will shift to where? To the left, exactly. So therefore, the concentration of ammonia will decrease while the concentration of nitrogen and hydrogen will increase, all right? So that's how you rationalize the changes that will take place, when you change the pressure of only one gas in the system, right? Because the concentration of the gas is directly proportional to the pressure, basically once you change the pressure, you change the concentration of the gas correspondingly, and therefore you can explain how the system will respond, all right? So that's what happens if you change the pressure of one gas. Now, what will be the case when you change the total pressure? Well, basically, the Chatelain's principle will apply. If you change the total pressure of the system, then the system will respond by doing the opposite of the change that you're imposing on the system. Now, how do we predict the direction of the shift as a result? Well, it's right here, actually, in the statement. It says when the external pressure is increased or when the system volume is reduced, because of course, you know that there's an inverse relationship between pressure and volume, right? So what will happen is that the equilibrium will shift in the direction producing the smaller number of moles of gas, all right? Because if you are increasing the external pressure, the system will reduce the total pressure by shifting in the direction which produces less gas molecules, all right? So applying that to the same equation here, I'm using the same reaction here, right? In order for you to make predictions in this particular kind of situation, right? What you'd have to do is look at the balanced equation. And again, this is, I can't stress this enough. This underscores the importance of having a balanced equation to begin with, right? So if you look at this system here, what you do is look at the stoichiometry and you look at the total number of molecules represented here. That's 3 + 1, 4 moles. And you look at the total number of moles of ammonia on the product side, and that would be 2 moles, right? So if you increase the total pressure, so if P total increases, what will happen is that the system will shift to produce less molecules. All right. So in this particular case, you have 4 moles here, you have 2 moles here. That means that the shift will be from left to right. So therefore, shift to the right. And therefore, as a result, the concentration of ammonia will increase and the concentration of nitrogen and hydrogen will decrease. All right. So if you want to favor, one of the things that you can do, if you want to favor the formation of ammonia, is simply increase the total pressure, right? And then the system will respond as described here. The system will shift in the direction producing, reducing the pressure by producing less gas molecules, which in this case, it means that it's going to shift from left to right, all right? And of course, if you understand that, then you should be able to explain what will happen if you were to decrease the total pressure, right? Which means that the equilibrium will shift in the opposite direction, producing more molecules, and therefore the concentration of ammonia will decrease and the concentration of the reactants, nitrogen and hydrogen, will increase, all right? So that's what happens when you change the pressure. Now, let me just say that in terms of the total pressure, that will be definitely so, what I just described, will be definitely true if it's a totally gaseous system, right? So these are all gases. If you have solids and liquids involved or aqueous solutions, then things are not as straightforward, and I won't get into that right now, right? So for problems where you're looking at changes in external pressure, basically you'll be given problems where the system is totally gaseous, right? That makes life a lot easier at this level anyway. Okay, let me clear this.
Question.
Oh, yes, ma'am. I'm sorry.
Will you always, when you're producing less, will you always shift it to the left, or it doesn't?
It depends on what you're
Okay,
trying to.
it just depends.
It depends, right? It depends on what you're trying to achieve.
Okay.
So let me.
And where it is on, like if it's on the product or reactant
Right,
side.
exactly. So like, for example, let me go back to this here. If your aim is to favor the formation of ammonia, which is what, well, you weren't here last time, but I was talking about this. Where my students, last time. If you want to favor the formation of this, then you choose a set of conditions which pushes the equilibrium to the right. If you want to favor the formation of NH3, right? So one of the things you can do is increase the concentration of nitrogen or increase the pressure, which increases the concentration of nitrogen, right? Because according to the Chatter's principle, the system will try to decrease the concentration of nitrogen by shifting to the right. The same thing is true if you were to increase the concentration of hydrogen. Same thing, it's going to shift to the right. Or you can increase the total pressure, right? And because of that, because we look at the total number of moles on either side. If you increase the total pressure, then the system will try to decrease the total pressure by shifting in the direction producing fewer gas molecules. So it's going to shift from 4 on this side to 2 on this side, right? So that's another thing you can do to favor the formation of ammonia, right? And another condition you can choose, as somebody mentioned earlier, you can decrease the concentration of ammonia. So if you continually remove the ammonia, again, Le Chatelier's principle will kick in, equilibrium position will shift to produce more ammonia, and therefore by so doing, you favor the formation of ammonia, all right?
Thank you.
Okay, so let me clear this. And let's see what is in the next line. Oh, very important. So this is interesting. What if there is no change in the number of molecules on either side, such as this reaction right here, right? You have 2 moles of gases on either side. Well, it turns out that it doesn't matter if you increase or decrease the total pressure, nothing will happen, right? And that makes sense, right? If you have 2 moles of gases on either side of the reaction, right? Then either increasing or decreasing the pressure will not make any change in terms of the total, the total pressure you can increase or decrease, but it won't change the equilibrium position, right? Because there will be no shift to a side which has less gas molecules because both sides have the same number of gas molecules, right? So in this particular case, as stated here, the equilibrium will not be affected by any changes in the total pressure, right? Now you can change the pressure of one component, right? So for example, what would happen if you were to decrease, let me write this down. What would happen if you were to decrease the concentration of iodine? How will the system respond? It will shift to the left, right? So therefore, the concentration of HI would decrease, and the concentrations of H2 and I2 would increase, all right? So you can change the position of equilibrium if you, in this particular case, change the pressure or concentration of one component, but if you try to change the total pressure, nothing will happen because you have 2 moles on either side, all right? Okay, so this is another example. This is the equation for this reaction here. Dinitrogen tetroxide reacting to form 2 moles of, and these are all gases, by the way. This is a gas, that's a gas, right? So basically here we have a mixture on this side here. We have a mixture, equilibrium mixture of both N2O4 and NO2. The pressure here is 1 atmosphere. And then all of a sudden, we double the pressure from 1 atmosphere to 2 atmospheres, right? So the total pressure is increasing. So based on that, which direction would you expect? Based on the balance equation here, which direction would you expect the equilibrium to shift? What? To the left, because you have 1 mole of gas here, and you have 2 moles of gases here, so therefore it will shift to the left, right? So therefore, that is what is being pictorially represented here. Basically what it's showing you here is that these 2 nitrogen dioxide molecules here and here will combine to form an N2O4 molecule. So therefore, the concentration of N2O4 will increase and the concentration of NO2 would decrease. So as stated here, 2 molecules of NO2 will combine to form a molecule of N2O4, and therefore the pressure would reduce after that. Okay, so that's just yet another example of Le Chatelier's principle being applied where you're changing the total pressure on the system. So the key thing you need to remember is that if you're given a question where they're asking for you to predict whether or not a reaction will take place, whether or not the equilibrium position will shift when you increase the total pressure, the first thing you should look for is the number of gas molecules on either side. That's the first thing you should look for, right? And then you go from there to make your prediction based on what the question is asking, all right? Okay, another factor that will affect equilibrium positions would be temperature changes, all right? And in this particular case, the first thing you look for in order to make such predictions is to see whether or not the reaction is exothermic or endothermic. And we all know what those two terms mean, right? An exothermic reaction is one that produces heat energy as you go from reactants to products. And the endothermic reaction is one that absorbs heat energy as you go from reactants to products. Another thing you need to remember is that if a reaction is exothermic going in one direction, then it's endothermic going in the opposite direction, and vice versa, right? So let's talk about how temperature changes affect the equilibrium position, right? So basically, let's say, and this is just a hypothetical example. Let's say you have A going to B, and let's say the reaction is exothermic. So delta H is negative or less than 0, right? Now, another way you can look at this, and this makes things a bit easier in terms of answering questions of this type, is that because heat is produced, you can rewrite this equation as A going to B plus the heat change, like this, right? So you can rewrite it like this, all right? In other words, you treat the heat as a product because the reaction is exothermic, right? It's producing heat, right? So let's say, and I think that's what they're saying here. Let's say you're increasing the temperature. So increase in temperature, right? So in order to increase temperature, what do we do? This corresponds to addition of heat, right? So all of a sudden, you increase the temperature by adding heat to the system. What does Le Chatelier's principle says? Whatever you do to the system to disturb equilibrium, the system will do the opposite to restore equilibrium, right? So if you're adding heat to the system, then the system will shift in the direction to reduce heat. Reduce the heat that is added, I should add. All right? So, if you're increasing this, right, and the system will respond by reducing it, that means that the system will shift in this direction. All right? So, if you add heat to the system, which is already exothermic, then the equilibrium position will shift from right to left, which means that the concentration of A would increase and the concentration of B would also, will decrease, all right? So that's basically how we can make predictions as to how temperature changes will affect the equilibrium position, all right? And this is just for the exothermic reaction, right? And we can use the same kind of rationalization for endothermic reactions. In fact, is it okay for me to clear this? All right, so let's look at what happens in a real example. In this case, I'm going to use N2O4 in equilibrium with NO2. We just looked at that. And I happen to know that this reaction is delta H positive, right? All right, so again, we can rewrite this. Now in this case, N2O4 to NO2. Because delta H is positive, what that means is that going from left to right, heat is absorbed. So in this particular case, I would put delta H on this side, right? Because heat is absorbed as the N2O4 reacts to form NO2. So here's my question to you. What would happen if the temperature is increased? Which direction will the equilibrium shift if all of a sudden you increase the temperature? It's going to shift to the right. To the right. Why? Because when you increase the temperature, you're adding heat, right? You're adding heat. So therefore what? If you're adding heat, then
To reduce it,
system will reduce the heat that is added. System will reduce the added heat which means that the equilibrium will shift to the right. All right? And therefore, I should add here, therefore, concentration of NO2 increases and the concentration of N2O4 will decrease. All right? And for those of you enrolled in my lab, you'll be looking at this reaction here. And this one, you can actually visually see the changes that would take place because NO2, this is a kind of yellowish brown color gas. And the N2O4 is a very pale green, almost colorless, right? And in the lab that you'll be doing, which involves this particular reaction, you're going to see that you're going to have the gas trapped in a test tube above a solution which produced it. And then you're going to put it in ice water, and you're going to see the color change. And then you're going to put it in hot water, and you're going to see the color change, right? And the color change is due to the fact that when you put it in ice water, the equilibrium will shift in this direction, right? And therefore, the mixture will look colorless or less brown. And then when you put it in hot water, the gas will look very brown, which is due to the shift to the other direction to produce NO2, all right? So that's basically how temperature changes will affect the equilibrium position of systems. So again, let me say that when it comes to answering questions involving temperature changes in equilibrium systems, the first thing you should look for is whether or not the reaction is exothermic or endothermic, all right? And that information would have to be given to you in the question, all right? Any questions about this? Any questions? Any questions? All right, let me clear this here. Let me see what else I have down here. Oh, okay, so that's temperature changes. The other factor that is being looked at here is whether or not a catalyst will affect the equilibrium position. And if you remember the role of the catalyst in the previous chapter that we talked about, the catalyst basically provides a different mechanistic pathway for a reaction of lower activation energy, right? And because the activation energy is lower, the reaction will proceed more quickly, right? And that's the kinetics aspect of catalysts, how catalysts affect the rate of reaction. Now, in terms of how it affects the equilibrium position, the key thing you need to remember is that the catalyst does lower the activation energy for both the forward reaction and the reverse reaction to the same extent, all right? So the result of that is that adding a catalyst will not affect the equilibrium position of a system already in equilibrium, right? So basically, if you have the system already in equilibrium and then you add your catalyst to it, the rate of both forward and backward reaction will increase at the same rate, right? So therefore, again, there will be no change in the equilibrium position, all right? Now, if you start off with the reaction before equilibrium, so let's say you just start off with the reactants, right? And you add the catalyst, then equilibrium will be achieved faster, all right? But the equilibrium position will not change, right? Between the catalyst or between the catalyzed reaction and the uncatalyzed reaction, all right? So as stated here, the catalyst merely causes the equilibrium to be achieved faster, but the equilibrium position itself will not change when you add a catalyst to the system already in equilibrium. Okay, so one more thing I want to say before we move on to some additional questions in your assignment. Let me just check something here. Okay, so let me just deal with this first and then we move on to the assignment. Very important for you to recognize. I think I mentioned this in passing before, but I'm going to emphasize this now, right? The only factor that is going to change the equilibrium position is temperature, right? Changes in concentration, changes in pressure, adding a catalyst will not change the equilibrium, the Kc or Kp value, or any Ks that we're going to meet later on, because you're going to meet some other K values like Kw, Ka, Kb. We're going to meet those later on. Regardless of what type of equilibrium constants we're talking about, The only factor that would change the equilibrium constant would be a change in temperature, all right? And we can make a prediction as to how the equilibrium constant will change. In fact, let me go back to this example right here. How did I write it? Did I put N2O4 as a reactant?
2N.
2NO2? I was just trying to remember which goes on what side, but okay. And as I said before, delta H here is positive, which means that delta H will be added to the reactant side. So let me so delta H is added here, right? So I think I said heat is added, right? In the previous slide, right? If heat is added, that means that according to Le Chatelier's principle, the equilibrium will shift in that direction, right? So the result would be that the concentration of NO2 will increase and the concentration of N2O4 will increase, right? Would decrease, I'm sorry. So therefore, since Kc is equal to concentration of NO2 squared divided by concentration of N2O4, what do you think is going to happen to Kc if concentration of N2O4 decreases and the concentration of NO2 increases? Then what's going to happen to Kc? Kc will increase. So let me just put that down here. Kc will increase, right? So basically what we're saying here is that if you increase the temperature of this system, then because the system, or because the reaction is endothermic, as it is written here, then that means that there will be a shift to the right, concentration of NO2 would increase, concentration of N2O4 would decrease, and therefore overall the Kc value will increase. So that's basically what is stated in this line right here. For an endothermic reaction such as this one, an increase in the temperature will shift the equilibrium position to the right, and therefore Kc or Kp or any other K, as I said before, that you're going to need will increase if it's an endothermic process. And of course, the opposite is true if the reaction is exothermic as written. All right. So remember again, temperature is the only factor that would affect the value or magnitude of the Kc or Kp or any of the equilibrium constants that you're going to need. All right. Okay. Any questions about what we just discussed here? Any questions? Okay. So, all right. So let's go to the assignment. So let me go here, 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 here. Assignment number 2. I'm sorry, assignment number 3. What am I saying? Okay, let me scroll down. And we have done all these questions already. Okay, so I'm going to skip number 4 for the time being because actually we should be able to do number 4. Come to think of it. So let's start. Let me just check the other ones below. 4, 5, 6. Okay, so we should be able to do at this juncture, we should be able to do questions 4 through 6. All right, so let me start with number 4. Number 4 says that 500 degrees Celsius, the equilibrium constant for the following reaction is 0.080. Given that ammonia is this, the concentration of ammonia is that, the concentration of nitrogen is that, and the concentration of hydrogen is that, find Q. So let's find Q first, and then predict how the reaction will proceed, all right? So if you remember, the equation for Q is basically the same as the equation for Kc or Kp or whatever. But the difference is that Q is basically for all the concentration terms to be at equilibrium or not. It doesn't have to be at equilibrium, right? So they gave you the concentrations here for the different components. So Q, I'm going to put QC to be more specific, will be equal to the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2Q, right? And then we put the numbers in. So in the case of ammonia, that number is 0.0596. squared, divided by the concentration of nitrogen, which is 0.600 m, multiplied by the concentration of hydrogen, which is 0.420 m, and this will be Q. So let's see what that gives. 0.0596 squared divided by 0.6 divided by 0.420 Q. Where's my Q sign? Here. And according to my calculation, this works out to be equal to 0.0799, right? So that's answering the first part of the question, what is Q? The next question is asking for you to predict how the reaction will shift at this stage, right? So in order for us to do that, we compare QC, which is this, to KC, which is equilibrium constant, which is this, right? And as you can see here, QC is slightly, very slightly less than KC, right? Because QC is 0.0799, KC is 0.80. So very small difference between the two, but still, QC is less than KC. Let me put in parentheses here slightly, right? Okay, yes, sir. Yes, ma'am, I'm sorry. No, because you have 3 sig figs here, here, and here. So you have to roll this out to 3 sig figs. You see what I'm saying? Now, if QC was exactly equal to KC, then there'll be no shift because the system is at equilibrium at that point, right? Okay, so the question is, how the reaction proceed? In other words, which direction will the equilibrium shift? All right, and because QC is less than KC, the equilibrium will shift in the direction so as to increase the QC value up to the KC value, which means that the reaction or the equilibrium system would have to shift from left to right so as to increase the concentration of ammonia and correspondingly decrease the concentrations of nitrogen and hydrogen so that the QC value will be equal to the KC value. So the answer is that the equilibrium will shift to the right. And again, I'm going to say slightly, right, because of the closeness between QC and KC. All right? Any questions? Clear my throat. Before I forget, because I tend to forget these things, let me get the attendance of people who came in late. Is Kane here? Yes, Kane is here. Leonard, not here. Heidi Medina? Here. Okay. Olano? Yeah. And Wright? Yeah. Yeah. All right. Okay, so let's move on to number 5. Okay, so in the case of number 5, they gave you the KC for the system, and they said if the carbon dioxide concentration is 0.15, that for water is 0.25, for hydrogen is 0.42, and for carbon dioxide is 0.37. Again, same thing, determine Q, right? So what is Q equal to? Let's hear what you have to say about it.
Q is the concentration of H2 multiplied by the concentration of CO2 over concentration of CO multiplied by the concentration of H2O.
Okay, very good. And then we put the numbers in, right? So in the case of hydrogen, it is 0.42. In the case of carbon dioxide, it is 0.37. In the case of carbon monoxide, it is 0.15. In the case of H2O, it is 0.25. Okay, let's see what this is. Okay, so according to my calculation, this works out to be 4.1. All right, so that's Q. And to be more specific, QC, right? So the next thing we do is compare the 4.1 to the 5.10. So that means that QC is less than KC. So which direction will the reaction shift? To the right. So therefore reaction will shift to the right. All right? Okay, any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Please feel free to step in whenever you have any questions. Because if Q is less than K, that means that the amount of reactants present in the system is too low for equilibrium, and the amount of products is too low, and the amount of reactants is too high. So the equilibrium, to achieve equilibrium, the system would have to shift to form more products and reduce the amount of reactants so that the QC becomes equal to KC, and therefore equilibrium is achieved that way. All right? I'm sorry, repeat that. We'll shift to the right, to achieve equilibrium. I'm sorry? No, that's what we are predicting based on the Chandler's principle. These numbers for the concentrations for the different substances are not equilibrium values. You see what I'm saying? So the system at this stage is not at equilibrium. What the question is asking is, which direction will it shift in order to achieve equilibrium? So if the QC value, we just plug the numbers in, which are non-equilibrium values. If we plug them into the QC expression and we find that it's less than KC, that means the reaction would have to shift to the right in order to increase the QC value so that it's equal to the KC value. You see what I'm saying? Right. And the opposite will be true. If QC is greater than KC, the reaction will shift in the opposite direction, so as to reduce the product concentration, increase the reactant concentration, and therefore the QC will decrease in order to get to equal to the KC value. All right? Okay, any other questions? Okay, let me here it is. Scroll down. Okay. Oh, okay. So this is, they gave you this equation here, right? And they're giving you different changes. And you're to predict, it says state and explain the changes. So you're going to state the changes and explain, the changes, basically, right? So this is the equation given. And if the temperature is constant, so there's no change in temperature, right? So it says in A, if you increase the pressure or concentration, same thing, of nitrogen. So basically, which direction will the system shift to? Okay, so shift to the right. So explain that using Le Chatler's principle.
Maintain the high equilibrium in the system must.
Let me start you off. If the concentration of N2 is increased, right? Then what?
Equilibrium shifted to the right to decrease
Right, so
concentration.
system equilibrium will shift to the right, to decrease the concentration of N2. And that's pretty much all I expect the answer to that question, right? So you're predicting the shift and then you explain, right? The shift is going to be to the right, and that happens because when you increase the pressure or the concentration of nitrogen, according to Le Chatelier's principle, the system will try to reduce the pressure of nitrogen by shifting the equilibrium to the right, and thereby reducing the concentration of nitrogen. All right? Any questions? Okay, so let me hear your response for B. In the case of B, you are increasing the pressure or concentration of NO. So what direction would you expect the equilibrium position to move? Is it to the left or to the right? To the left. So shift to the left, right? So let's hear your explanation. Let me start you off again. If the concentration of NO increases, then
Systems equilibrium will shift to the left,
equilibrium,
decrease the concentration of.
exactly, equilibrium shift to the left to decrease the concentration of NO. All right? Any questions? Okay, I take it's okay for me to clear this. Okay, so let me clear this. Let me scroll down. Okay. Interesting. Total pressure is increased, and let me rewrite the equation up here since it's. Okay, so this is the equation here, N2 plus O2, you gave 2 NO. And these are all gases. Okay, so if the total pressure of the system is increased, what would you expect to happen in this case? What do you look for? Remember what I said you look for when you're increasing the total pressure?
The moles.
You look for the number of molecules on either side in the balanced equation, right? So how many molecules do you have on each side? How many total molecules do you have on the left side? 2. And how many do you have on this side? 2. So guess what? There will be no change, right? So therefore, no change.
Because it's already at equilibrium, right?
I'm sorry?
Does that mean that it's already at equilibrium?
Right, exactly. It's already at equilibrium and you change the total pressure. Excuse me. So because of that, because of the fact that you have 2 molecules of gases on either side, that means that there will be no change in the equilibrium position because the reaction is, and the term we use for this, I probably should have told it before, the reaction is equimolar. That's what that means. An equimolar reaction is one that has the same number of molecules on either side. All right? Okay. Any questions about this? Any questions? Okay, what about D? The total volume of the system is increased. So all of a sudden, you increase the volume of all the gases in that mixture, right? So my question to you is, which direction would you expect the equilibrium position to shift?
Decrease the concentration of one.
Well, you're decreasing the concentration and also you're decreasing the pressure of the entire system as well. So if you increase the volume, think about it from Boyle's law. There's an inverse relationship between pressure and volume, right? So if you increase the volume, the total pressure is going to decrease. So what's going to happen if the total pressure is decreased? No. I'm sorry? No. What I'm asking for is what would happen to the equilibrium position when the total pressure is decreased as a result of increasing the total volume?
It would decrease
No. Which direction will the equilibrium?
It,
Will it shift to the left? Exactly, nothing will happen because the reaction is equimolar. So basically, the same answer in C is the same answer in D. Right? The answer for C, I'm sorry, the answer for D is the same as the answer for C. No change because you have equal molecules of gases on either side. Remember I said that for equimolar reactions, no change in pressure will affect the equilibrium. It doesn't matter if you increase or decrease the pressure. And it doesn't matter if you increase or decrease the volume, right? The equilibrium position will not change, so therefore there will be no changes in the amounts of all the gases in the system. Okay, so that's D. What about E? Adding a catalyst. No change. For a different reason, but no change, because remember we said that when you add a catalyst, you're increasing the rate of both the forward and reverse reaction to the same extent, right? So therefore the equilibrium position will not change. So no change because the catalyst will increase the rates of both forward and reverse reactions. All right, so as a result, there will be no change in the equilibrium position. Okay, and then the last one, shoot, what did I? Okay, I'm going to clear this and scroll down to F. Decrease the concentration of O2. So let me rewrite the equation here. The equation is N2 gas plus O2 gas to give 2NO gas. All right, so what happens if you decrease the concentration of O2? Which direction will the equilibrium shift? And of course, the explanation. So let's deal with the direction first. Which direction will the equilibrium shift when you decrease the concentration of O2? Shift to the left, okay? And how do we explain that?
To decrease, the equilibrium shifts to the left to increase.
Okay, so if the concentration of O2 decreases, the equilibrium will shift to the left to decrease. Well, let me just put O2 to increase, I'm sorry, the concentration of O2, right? And that's how you answer that, right? Okay, any questions about this one? Any questions? Yes, sir.
I had a question about E. When it said the total volume of the system increased, so what would happen if the reaction wasn't
Oh, okay, and we did some examples of that before. If you remember the N2O4 going to NO2, we have 2 here. So remember, we look for the number of molecules on both sides. We have 1 here, we have 2 here, right? So if you were to increase the total pressure of the system, that means that the system will shift in the direction producing fewer gas molecules, right? So it's going to shift in this direction here. And therefore the concentration of N2O4 would increase and the concentration of NO2 would decrease. All right? Okay, any other questions? Any other questions? Any other questions? Okay, let me clear this. I think that's all we can do for now. Yeah, okay. So let me go back to the PowerPoint and let's talk about, okay. All right, so these are, some more questions at the same time. Okay, so the first one, they gave you this equation here. And they said that you have a mixture at equilibrium already, right? It says an equilibrium mixture of O2, SO2, and SO3. And basically, it was originally in a 1 liter flask, and then all of a sudden you transfer it into a 2 liter flask. So the question is asking, in which direction does the net reaction proceed to restore equilibrium? And it gives you the equation, right? So how would you tackle this one? You should be able to do this one based on what we just looked at in the assignment. Which direction will the reaction shift?
To the left.
To the left. Why do you say that? Look at,
There's less than both on the left side.
oh, okay. So you have 2 moles here, and you have 3 moles here, right? So actually, he's not right. Because there is an increase in volume, which means that there is a reduction in the total pressure, which means that what? It's going to shift to the right, producing more gas molecules, all right? Yeah, so somebody tell him when he gets that. So again, remember there's an inverse relationship between pressure and volume, right? So if all of a sudden you increase the volume, you reduce the total pressure, the system will try to increase the total pressure, and therefore the system will shift in the direction producing fewer gas molecules. And therefore, in this case, it's going to shift from left to right, all right? Okay, and then this one here has to do with whether or not, okay, is the amount of NO formed greater at higher or lower temperature? Okay, so basically, you're to tell whether or not you can favor this formation of NO according to whether or not the temperature is high or low. And here's the hint right here. The reaction is endothermic, right? Which means that you can write it like this, where the change in heat can be seen as a reactant for the purposes of solving this problem, right? So based on that, which would favor the formation of NO? High temperatures or low temperatures?
You said endo?
It's endothermic because delta H is positive, right? Which means that the heat would be added to this side of the equation. So remember, if you're increasing the temperature, you're adding heat to the system. If you are reducing the temperature, you're removing heat from the system, right? So which one of those two would favor the formation of the product nitrogen monoxide?
The high temperature.
Exactly. So basically, high temperature implies increase in delta H, which implies a shift to the right. All right? And therefore, NO, we just write down here, favoring formation of NO. And that's how we answer that, all right? Okay, any questions? Any question about this one? Any questions? Okay, so let's talk about some quantitative aspects of equilibrium. So we can determine, of course, the equilibrium constants experimentally if we know what the concentrations are at equilibrium, all right? Now, typically what we would do is start off with the initial amounts of one or more of the species, and then we determine the amounts at equilibrium, and then we calculate the concentrations and plug them into the equilibrium expression, and that would give us the Kc value, right? So the approach that is generally useful for doing this is we determine the concentrations of all the components present before equilibrium, and then we determine the changes in the concentration as the system is moving towards equilibrium, and then based on those two, we can determine the concentrations at equilibrium. So we usually design a table which is nicknamed ICE, which stands for Initial Change in Equilibrium, all right? So the best way to learn this, of course, is to go directly into an example. So we're going to look at this example right here. This question says that you have a 10-liter vessel, you give the temperature, and it gives you the amount of SO2 and O2 present, and they react, and at equilibrium, you're going to end up with 0.162 moles of SO3. So the question is asking, what is the Kc for this reaction right here, all right? So the first thing you need to do is determine the initial concentrations of everything before, and then the changes, I'm sorry, you need to determine the concentrations of everything before equilibrium, and then the concentration of everything after equilibrium. So let me just show you how this is done. So this represents the initial state, this represents the equilibrium state. So initially, the concentration of SO2 would be equal to the moles of SO2, which is 0.250 moles, divided by 10.0 liters. So that would be equal to 0.0250 M, all right? So that would be the concentration of SO2 initially, and then the concentration of O2 initially would be equal to the moles, which is 0.200 moles, divided by the same volume, because they're all in the same container, so they will all occupy the same volume, right? So this would be equal to 0.0200 M, all right? So those would be the initial state. Now, at equilibrium, the only thing that they gave us is the moles of SO3, right? So we can calculate the concentration of SO3 at equilibrium. That would be equal to the moles, which is given as 0.162 moles, divided by the volume, which is 10.0 liters, and this will be equal to 0.0162 moles. Or, I'm sorry, not moles, M, all right? Okay, so this is how we set up the ice table. Initial, change, equilibrium, right? What we do first is write down the initial concentration values here, which we just calculated for the SO2 and the O2, right? So for SO2, it's going to be 0.0250 M, and for the O2, it's going to be 0.0200 M, and for the SO3, nothing, because there was no SO3 there to begin with, right? Then down here, let me draw lines to separate the rows. Now, we don't know what the changes are yet, but we do know that at equilibrium, the concentration of SO3 is 0.0162 M, all right? So that's all we know based on the concentrations that we calculated over here on the right side. Based on the fact that we started off with 0 M of SO3 and 0.0162 M of SO3 at equilibrium, we can determine the change. The change will obviously be plus 0.0162 M, right? Because you're starting with 0 before, and then at equilibrium, you end up with 0.0162 M, all right? Now, based on the amount of product that is formed, we can determine, based on the stoichiometry of the equation, we can determine the changes in the concentration of SO2 and O2. Now, there's a 2-to-2 mole ratio between the SO2 and SO3. So the change in the concentration of SO3 is plus 0.0162, which means that the change in the concentration of SO2 would be minus 0.0162 M, right? Minus because, of course, the SO2 is reacting, right? And then as far as the O2 is concerned, there's a 1-to-2 mole ratio between the O2 and SO3, which means that the change in the concentration of O2 would be minus, draw a line here to separate these, minus 0.0162 M divided by 2, right? Because for every 1 mole of oxygen that reacts, there are 2 moles of SO3 that is produced, all right? And therefore, because we know the changes here and here, we can determine the equilibrium concentrations here and here, right? So as far as the SO2 is concerned, the change or the equilibrium concentration of SO2 would be 0.0250 minus 0.0162. And according to my calculation, this works out to be equal to 8.8 times 10 to the minus 3 M. And then as far as the O2 is concerned, that would be 0.02 minus 0.0162 divided by 2. So according to my calculations, this works out to be equal to 0.0119, right? And then now, remember now, the question is asking for Kc. Kc expression based on this equation is going to be concentration of SO3 squared divided by the concentration of SO2 squared times the concentration of O2. And then all we have to do from here is plug the numbers in. So for SO3, that would be 0.0162 m squared divided by 8.8 times 10 to the minus 3 m squared multiplied by the concentration of O2, which is 0.0119. And then we do the number crunching, 0.0162 squared divided by 8.8 times 10 to the minus 3 cubed. Oh no, squared, I'm sorry. And then divided by 0.0119. Okay, so according, hold on, let me do this again. I think I may have made a mistake somewhere. 0.0162 squared. 8.8 squared. 2. Okay, so the answer I got rounded off to 2 sig figs would be 280. All right, so that's basically what I got. If I made a mistake and you identified a mistake, please let me know. All right, but that's what I got. All right. I'm sorry. Oh, no units for Casey. Right. Right. Remember, for all the K's that you're going to meet, no units. All right. Okay. Any questions? Oh, yes, sir.
For O2, where does the M go?
Oh,
0.
yeah, there should be an N here. Yeah. Yeah. And here as well. Okay. Any other questions? Any other questions? Okay. So moving along. All right. Now. What time is it, by the way? Okay, we should be able to do this. So what we have just done is determine Kc based on changes in concentration before and after equilibrium. Now, doing the reverse, in other words, if you're given a Kc and to determine the concentrations of the different components at equilibrium based on pre-equilibrium concentrations, that's a bit more complicated, but we're going to do that here, right? We're still going to use an ice table, but this time it's going to be a bit more challenging. And the best way to, of course, do a question of this type or learn about this is to go directly into a question of this type. So they gave you the equation, they gave you the Kc value, and they gave you the amounts of the reactants to start off with. They gave you the volume of the vessel, and the question is asking how many moles of each gas will be present at equilibrium. So the first thing I will do is I will determine the concentration of each gas. So just to utilize as much space as possible. First thing I recognize here, the first thing that jumps out at me is that the moles of both gases are the same, right? And they are both in the same volume in terms of the container. So basically, we can kill 2 birds with 1 stone and calculate the concentration of each of them, which will be the same, right? So the concentration of hydrogen and iodine will be equal to 0.500 moles divided by 5.25 liters, right? So let's see what that gives. 0.5 divided by 5.25. So according to my calculation, this works out to be equal to 0.0952 M, all right? So the next thing I would do is set up an ice table. So this is the equation right here. HI gas. So the initial concentrations of the H2 and the I2 would be the same, which is 0.0952 M. And this is 0.0952 M. And of course, there's no hydrogen iodide to begin with. Now, as far as the change is concerned, we don't know what that is, right? So I'm going to say that let X represent change in concentration of H2, right? So if that's the case, and I think that is kind of worded incorrectly. So let me just say, what? Let me express it this way. Let X equal to concentration of H2 reacting, right? So if that's a change, if that's the amount of H2 reacting, the concentration of H2 reacting, that means that the change as far as H2 is concerned would be minus X. Because of the 1-to-1 mole ratio for iodine, that would also be minus X. But because you have a coefficient of 2 here, so that's a 1-to-2 mole ratio between the H2 and I2, this is going to be plus 2X. Of course, this is plus because HI is being produced. So at equilibrium, you're going to have 0.0952 minus X here for the equilibrium concentration of H2. The equilibrium concentration of I2 will be the same, 0.0952 minus X. And then here is going to be 2X because 2X plus 0 gives you 2X. So we're going to plug these terms into the Kc expression, which is Kc is equal to the concentration of HI squared divided by the concentration of H2 times the concentration of I2. And then we put the different terms in. HI concentration is 2X. We square that divided by concentration of H2 times the concentration of I2. These two are the same. So basically you can simplify this to 0.0952 minus X squared. All right. And that we set to be equal to the 54.3. So basically from here, it's all algebra in terms of determining the final answer.
Quick question.
Yes, ma'am.
What did you mean when you said let X?
Right. So what I'm saying here,
Reacting, what did you mean by that?
right. So we don't know what the amount of H2 reacting is. Right? We don't know because we only given the initial, or we only determine the initial concentrations, right? We don't know what the equilibrium concentrations are. So what we did is that assume that X represents the amount of H2 that reacted in terms of the concentration. If we assume that, then the change for H2 would be minus X, right? Because
What are we assuming?
huh?
What are we assuming?
We're assuming that X is the amount of H2 that reacted,
Okay.
right? So basically the change in the concentration of H2 will be minus X. And because of the 1-to-1 mole ratio between the H2 and the I2, that change also will be minus X.
Okay.
And because of the 2-to-1 ratio between the HI and the H2, the change is plus 2X for the HI. And then we add this line to this line, and that gives us this line right here. Right? Which gives you the expressions for the concentration of different terms. Yes, sir.
Would it matter?
No, it wouldn't matter. It might look a bit different, but the result should be the same. All right? Because you could have said, okay, let HI represent, I'm sorry, let X represent the amount of HI that is produced, right? So if you did that, this would be X, and then this would be minus half X here and minus half X here. But the result should still be the same, all right? So, oops, sorry. Okay. So, okay. So basically, we have to solve for X in this equation right here. So since I'm going to need some more space, I'm going to erase some of the stuff on top. Okay, so the first thing I'll notice in this equation here is that the first thing I notice is that we have 2x squared up top, and all of this here is squared here. So basically, if you find the square root of both sides, right, you're going to end up with 2x divided by 0.0952 minus x, and that will be equal to the square root of 54.3. So 54.3 square root. So according to my calculation, that gives 73.7. I'm sorry, 7.37. 7.37, right? And then what I will do, of course, is cross multiply. So you're going to get 2x is equal to 7.37 multiplied by 0.0952 minus x. And then expand this part here. So you're going to get 2x is equal to, let me see, 7.37 times 0.09, oops, 7.37 times 0.0952. Okay, so this part will work out to be equal to 0.701. I'm sorry, 0.702. And then minus 7.37x. And then what I will do next is add 7.37x to both sides, so that this goes with that, and the result will be 2x plus 7.37x is equal to 0.702. And then when you add this to this, you're going to get 9.37x equal to 0.702, which means that x is equal to 0.702 divided by 9.37. Divided by 9.7. So according to my calculation, this works out to be round off to 366, so this will be 0.0749. Now, we're not finished yet, because what we have calculated here is x, right? X is the change in the concentration of H2 and I2. And remember I erased it, but remember we said that the concentration of H2 at equilibrium is the same as the concentration of I2, sorry, concentration of the risk. This is gone. Okay, concentration of I2 is equal to, what was it, 0.0952, right? Minus x, right? And the concentration of HI would be equal to, was it 4x squared, right?
I think it's 2x.
Yeah, it's 2x squared.
2x. Actually, yeah. All right, so basically, once we find x here, we plug that value of x into this expression and this expression, right? And that will give us the concentrations in each case. So again, I need to do some erasure here to get some more space. So let me just erase that here.
So you put that number back into the concentration
Exactly.
of,
Right, so in the case of concentration of H2 and I2, same calculation for both of them. So the concentration of H2 is equal to the concentration of I2, which is equal to 0.0952 minus 0.0749. And this is M and M. And this will be equal to 0.0952 minus 0.0749. So according to my calculation, this works out to be equal to 0.0203 M. And then to calculate the concentration of HI, that is equal to 2x, right? So 2 times 0.0749 M, 0.0749 times 2. So that would be equal to 0.14. How many sig figs? 3 sig figs. So that would be 0.150 M, right? And so those are the molarities, and we're not finished yet because the question is not asking for the molarity. The question is asking for the moles, right? So I need more space down here. So the moles of H2 at equilibrium. Number of moles of H2 will be equal to the number of moles of I2. And that's because they have the same molarity, which is 0.0203 M, which is the same thing as moles per liter, multiplied by the volume of the container, which is 5.25 liters. So 0.0203 times 5.25. So this will give 0.107 moles. And then for the number of moles of HI, that will be equal to what we have here. So that would be, no, not there, I'm sorry. That will be this, which is 0.150 moles per liter. Again, divided by the same volume because they're all in the same container. So 0.150 times 5.25. And according to my calculation, this works out to be equal to 0.788 moles. And these, ladies and gentlemen, would be the final answer. All right? Any questions about this? Any questions? Okay, I think I'm going to stop here. Let's just see what the next slide. Okay, I'm going to stop here for now. And yeah, because that's another long one. So just to remind you, test tomorrow. I don't know if you guys saw the announcement I posted last night. I forgot to tell you guys that the test will be 75 minutes long, right? So it's important that you get here on time so that you can start the test punctually. And then after the 75 minutes, then we'll have our regular class. We will continue our discussion of equilibrium. All right. Also, I didn't announce this, but I decided today that I'll make myself available tomorrow in the morning from 8 to 11. I'll be in my office, but of course you can call me or we can make a Zoom link and you can contact me during that time so that if you have any questions, any last minute questions about the test, I'll be available for that. All right. Okay, so that's it, folks. Yes, sir.
So the active side for the company, if they have less, the holes than the project side, they're both going to be negative.
No, if the reaction is going in that direction, so you have H2 reacting with I2. That means the change in the concentration for the H2 and I2 will be negative because they're being used up. And the I2 and the HI is produced, so it's positive. Same thing here. See this? If the reaction is going in that direction.
Yeah.
Exactly.
How do we tell?
Well, in this case here, let me go back to this slide. We'll just remove all the same too. In this case here, they gave you the initial state. In the initial state, you only add SO2 and O2, nothing else is present. And then at equilibrium, you have SO2. So obviously, the SO2 is going to react with the O2 to produce SO2. All right?
And on here, I think it said in the words that it starts with. Right?
Exactly. Right. Exactly. Yes, ma'am. Oh no, don't follow. You'll be answering all 3 questions. Right, so I think that was the whole test. He said something like, if you answer. What did he say? If you answer two. Right, mistake, forget that. My, your answer, no, I think better. Right, that's it, yeah. Yes, ma'am. Good luck. Right, I got that. Oh, yes. Yeah, I got it though. I'm in the middle of grading it. Yes, sir. Yeah, but the test. Yeah. Mhm. Yes, sir.
I had a question about today's present. So basically, like, when you're finding like the
That's
square
right,
footage, so you need to put in like 1 sig feet or 2 sig feet?
I do two sick things, yeah. Yeah, that would.
Because when you're calculating this, I was getting like different numbers.
Right, yeah.
And all that, so I.
Yeah,
kept
but it looks like you did the right thing
Okay,
here. Yeah,
alright, thank you.
Wait, even for like the 50 seconds, there would still be 2 sig figs?
yeah,
Like what?
it makes it more accurate, you know, if you do two sick things, which I think is what he did.
Yeah.
Oh,
So for 8 seconds to do 2 sig figs?
Yeah.
What else?